Hello everyone, I am Samiha. I am a fourth year PhD student at Northern Illinois University. This is a collaborated work with our colleagues in Northern Illinois University and MIT Lincoln Laboratory. I am going to present VulSim. It's a function level software vulnerability detection tool. We noticed that existing data sets are not enough to train a deep learning based model, so we leveraged similarity of multidimensional neighbors to detect if a piece of code is vulnerable or not. Before going into detail, let me ask you a question. How does a sad deep learning model look like? Or what makes a deep learning model sad? Okay. Why don't we ask AI itself? I asked AI and this is what I got. A deep learning model, when it's fed with only a limited amount of data, this is how it looks like. Then I asked AI, how does a happy deep learning model look like? This is what I got. So, a deep learning model, when it's fed with a huge amount of data, this is how it looks like. We do not want any sad deep learning model. We only want happy deep learning model. Now the question is, what's the challenge? What's the limitations? Why cannot we get a happy deep learning model in software vulnerability detection domain? The answer is simple. We do not have enough data. Yes, that's the problem. Several data sets do exist. We have National Vulnerability Database NVD. It contains around 250,000 records. But as we already know, deep learning models are data hungry, so even if these records are not enough to train a deep learning model efficiently. Moreover, several studies demonstrated when we try to use data in real life application, we need to do some pre-processing and we have to fetch records from their GitHub repository. Throughout the process, we only left with a limited number of vulnerable samples. So, NVD alone cannot be used to train a deep learning model efficiently. We do have software assurance reference dataset served by NIST. As we know, it contains synthetic samples and several studies demonstrated models trained on synthetic data do not perform well in real life application. So, SARD alone cannot be used to train a deep learning model efficiently. We do have recently released diverse val dataset. It merges several existing datasets. Additionally, they also incorporated their own samples. Even if merging all these records, the total number of records in diverse val dataset is only 41,000, which is once again not enough to train a deep learning model efficiently. So, a robust solution is required to deal with this dataset issue. What could be the solution? Let's think about it. Okay, here's the idea. There is an old saying, you are the average of the 5 people you spend the most time with, which means your surroundings, your friends, your neighbors define who you are. Now the question is, can we leverage this knowledge to detect if a piece of code is vulnerable? Fortunately, the answer is yes. This is how. Once again, I took help from AI to draw this image. In the center, we can see a C function. It's surrounded by its neighbor. As we can see, some of the neighbors are vulnerable and marked as red. And some of the neighbors are safe and they are marked as green. Now, what we are trying to do, we are trying to check how many of the neighbors are vulnerable and how many of them are safe and how similar they are. Based on this information, we are trying to detect if a piece of code is vulnerable or not. Now, when we are considering this neighbor information, we are considering several dimensions. The first one is semantic dimension. So here we can see two pieces of C functions, and as we can see, they are sharing similar semantics or terms. When this type of situation happens, we can say that these two functions are semantically similar or similar in semantic dimension. And what we also noticed, When two functions are similar in one dimension, they might also share similar types of vulnerability. In this case, both of them are sharing stream-related vulnerability. The next dimension is contextual dimension. If we look at the highlighted portions, we can see both of the functions are storing information to buffer. That means they are sharing similar functionality or contextuality. This means they are similar in contextual dimension. And once again, both of them are vulnerable to memory buffer related vulnerability. The third dimension is syntactic dimension. If we look, these two functions look alike. They have one return type, no parameter, and one line of function body. So these two functions are syntactically similar, and once again, they are sharing memory buffer related vulnerability. Another term I'm going to use, in fact, I am using it a lot. I'm saying two functions are similar. When I say two functions are similar, what does it mean? It means they are similar in terms of cosine similarity metric. What is cosine similarity metric? This is the formula. It looks so scary, let's get rid of this. Once again, take help from our friend AI. In the center, we can see a piece of C code, and some of the neighbors are staying closer, which means they are having a cosine similarity closer to 1. Some of the neighbors are in distant position and their cosine similarity is closer to 0. So this is the metric we are going to consider. Now we have all the backgrounds. Now I'm going to show you the proposed approach. We have a limited amount of data in number of functions. What we can do, we can feed it to a deep learning based model, and from that we can extract the neighbor information. As we already know, some of the neighbors might be vulnerable, some of the neighbors might be safe. When we consider this neighbor information, we can consider either semantic properties or contextual properties, or we can consider the neighbors in syntactic dimensions. Or what we can do, we can merge neighbors in all three dimensions and extract set of features. The detailed process of how we are extracting these features, due to time limitations, I cannot explain here. I would like to recommend you to go through the paper. Once we have this set of features, we are simply feeding it to a decision tree based classifier which marks the record as either vulnerable or safe. Now, when we are considering these three sets of properties, we are leveraging three existing deep learning based models. For semantic dimension, we are considering existing sentence BERT model. For contextual properties, we are considering code-to-vec model. For syntactic properties, we are utilizing existing code-BERT model. So we utilized multiple dimensions for the same data. We are also utilizing neighborhood information. What we are achieving? So we are addressing the dataset limitation of the current approaches. Now once we have the proposed approach, I am going to show you how we evaluated our approach on defined dataset. Here, these are the accuracies of the original models without any neighbor information. Then we applied neighbor information in single dimension. Then we applied neighbor information 2 dimensions at the same time. And finally, our approach VulSim, where we merge 3 dimensions at the same time, and as we can see, it achieves an accuracy over 75%. We also compared our model with existing Codex Glue benchmark by Microsoft. What is Codex Glue benchmark? It's a platform where we can compare our model with other models in several natural language processing tasks. Here we compared our approach VulSim with other models in defect prediction task, and as we can see, the topmost leader in the Codex Glue benchmark is having an accuracy of around 69%, where VulSim, our approach, has an accuracy over 75%. This demonstrates the strength of incorporating neighbor information in multiple dimensions. We also compared our approach with other state-of-the-art vulnerability detection tools, and as we can see, VulSim outperforms other models in terms of accuracy, precision, and recall. Finally, we test for generalizability, and we trained VulSim and other models on Divine dataset, and we tested it on Big Val dataset. And once again, VulSim outperforms other models in terms of accuracy, precision, and recall. In summary, we pointed out that existing datasets are not enough to train a deep learning-based model efficiently. We propose VulSim. It incorporates multiple dimensions, and it also incorporates neighbor information. Experimental results shows VulSim outperforms other state-of-the-art techniques and shows enhanced generalizability. For more details, I would like to recommend you to go through the paper, and finally, our artifacts are available online. Thank you, and let me know if you have any question.